So, PStats is the Panda tool for measuring performance statistics. Built into very low level Panda. It does a top-down performance analysis of Panda, of a runtime of your frame time, where your time is spent in a frame. Excuse me. It used to be only on Unix. We used to have a PStats viewer on Linux and on SGI IRIX. And for a long time, that was the only way you could run PStats, and so most people didn't bother. Now we've got a port of the PStats client onto Windows, so you can run PStats on your Windows machine. And so everybody should be running PStats. You shouldn't have any excuse for running code that doesn't perform up to expectations. So let's talk about what it is first. PStats is a program. It's client server actually. There's a your server is Panda. When you run Panda, you are running a PStats server. No, sorry, I got it wrong. When you run Panda is a PStats client. When you run Panda, you're running a PStats client. The server is actually a separate executable that you start up. And it's confusing, and even I got it wrong just now. But normally, you think of a client as something that you run on your own machine, and the server is something that is somewhere else. In this case, it's kind of like the X server. The server is something that's just serving up Windows. The PStats server is serving up graphs in this case. So the client is Panda, it's running, it's doing stuff, and when it contacts the server, it says, give me a graph that shows my performance. So to start up PStats, you first start up the PStats server, and it could be a process. It's just a process that sits in the background. I've got it down here. You can't see it, but it's this little task down here on the bottom. I've already started. It's just a program called PStats. It happens to live in Panda tool. You run it. It runs in the background. Doesn't do anything. Let's see. What it actually does is listening on a TCP port, which shows right here. The default port is 5180. That's in your configure.c file. You can change it. It waits for a connection from a Panda client. Now, a Panda client could be running on the same machine or a different machine. I'll run it on this machine. First, we'll start with preview. Good old preview. We've all seen the silly little triangle. And when you run preview, there's one hotkey that you can use, Shift-S, to contact the PStats server if it's available. S for stats. And here it is. Here's a PStats window. As soon as Panda contacts the PStats server, it opens up a window for all the connections from this particular client. And I could have connections from multiple clients at the same time if I wanted to. There'd be two different windows. Within this window, I have a graph. This is the first graph it gives me by default, and this is a strip chart that just shows everything that Panda's doing. The labels are, of course, a little hard to read on the display here, but top in gray it shows frame, which is the overall frame time. Then we have app, draw. And the colors are color-coded. So the app is green, col is yellow, and draw is red. And what we see here is this frame time is almost entirely draw. There's some junk going on up here, but that's just, I think those are just spikes of red that you can't really see very well in the video. Those are actually very small peaks of red instead of pink. There's no pink. Now, in fact, preview is rendering almost nothing. It's just a silly little triangle. So it's surprising that we're spending all this time at all. It says up here we got 19 milliseconds in each frame. Well, that's actually the video sync rate. Preview won't render any faster than the video rate. And if we double-click on the draw and decompose it, if we double-click on the draw column, it decomposes what the draw time is into all the things that make up draw. And you see here, draw is the main category. This reminds us that we're viewing draw. Make current is the time to make the current graphics context current. Clear is for clearing the flame buffer. Flip is to flip the back and the front buffers. And bins is for drawing actual individual bins. And again, we see the time is almost entirely in flip. That's consistent with the video rate because it's at the time that we call flip that it actually has to wait for the next video sync. So we've got Panda is basically doing nothing at this point. Spending all its time in flip, as we expect. Now the frame rate here is conveniently written up here in the corner. We see this is 19.2 milliseconds or 52.8 hertz. It's a little bit slower than 60 hertz because Windows has a problem with scheduling. When I have a window on the desktop, it doesn't always wait for just one sync. It might skip a couple of frames. That's a bit of a problem with the graphics driver and with Windows interoperating together. If I were to run it full screen, it would sync much better on 60 Hz. We could actually get a solid 60 Hz frame rate. But anyway, so that's the basic gist of how to use PView. You see, you get the script here, which is kind of nice. And any one of these categories, you can generally drill down. There's nothing much more to see here in just a blue triangle, but if I wanted to see where all the time in bins was, all that time, well, gee, we're spending almost no time drawing opaque bins and almost no time drawing transparent bins. Isn't that exciting? I can go back up, and there's no more to see about flip. Flip is just flip. There is some almost no cull time. So let's look at a more interesting model.
Good question, David.
Yes?
How do I cull it when I blew the graph away? How do I collate graph to those columns you have? I'm looking at cull, I'm looking at... What's the graph showing?
Oh, I'm sorry. Yeah, this is a bit of a... I just jumped right into it. Okay, so this is time going by. Each vertical slice of the graph is an instant in time, one frame really. And during the frame, the amount of color represents how much time it's spent in that particular task. So I can see that, in fact, let me pause the graph.
It's a lot easier to see once you have more colors.
Yeah, that's true.
Do want
to. I'll put some more. Yeah, let me bring up another model. Just a more interesting model. Let's see. So about HQ exterior. Okay. This is just a static model, so there's not going to be a whole lot going on interesting in the graph. And it's hard to see in the dark image, but this is the model of the exterior of the Silvat factory. And again, we'll bring up the stats graph. And now, of course, again, and this will always be the case in PView, it's almost entirely draw, because PView doesn't really do anything. But within the draw task, we can see a bit more going on.
Okay, so they'd be stacked. If there was, the other ones were so small.
Right.
That's why I was blown away that they're all red. I couldn't tell them. I get it.
Yeah, and let me make this a little bit bigger too. Okay. So here we can see significant time being spent here in bins. This is all the stuff that we're drawing, and this is flip. Again, we're spending most of our time waiting for video sync. So we can draw the entire scene in less than one frame, 160 Hz frame. But yeah, so we can see it's spending this amount of time in drawing this.
Now it makes sense.
This is actually drawing.
Yeah.
Here is just wasted time in flip.
Sorry.
Yeah, that's fine. And we can ask questions like how much time am I actually spending in bins. You can bring a little guide bar up, and the number over there says it's 4.7 milliseconds. If you care about that, I'll get into details like that in a minute. Okay. Now let's get into something much more interesting. We start up. Actually run Toontown. Now, this time, when you input showbase, it respects a configure C variable called want PStats. PView doesn't respect this because I figure that you don't really want to bring up a PView or PandaStats viewer every time you launch PView. You're just looking at model. But if you set want PStats true in your configure C, then every time you launch showbase, it'll automatically start the PStat. If you don't specify want PStats, you can still start at runtime with the import PStat client, PStat client connect. Okay, here we go. We finally got loaded up, and we're running Toontown in the background. And now, again, we see mostly draw, but we see some other interesting colors going on up here too. We see some significant time in call, some time in app. So let's look at those a little more closely. Right, so the call here is this yellow color. This is the time that it takes Panda to traverse the scene graph, figure out what all the nodes are, and figure out what the states are. Then it passes it to draw, which is this big red thing. Probably, I'm guessing now this big red thing is mostly not flip. It's mostly actually sending vertices down, but we can take a look at it. An app is everything. It's basically everything else in Python, where it's calculating collisions, doing the smart camera update, moving the clouds around, moving Mickey around, stuff like that. And we can double click on any of the categories. We can actually click on the left here on these things, or we can actually click on the graph itself. For instance, let's see where the draw time is spent. Okay, actually there is significant time spent in flip still. So the time spent drawing all these vertices is not so big. Incidentally, So this flip is still waiting for the video sync.
We're not double buffering?
We are double buffering, but still we have to
Still
wait.
takes so much to flip. Wow.
Well, 60 hertz. This
You're
is
ahead of your frame rate, or?
this is 60 hertz right here. So we're actually running about 45 hertz right here, or 20 hertz. So we have to wait for the next harmonic of 60 hertz. So it'll be 20 hertz. If we wanted to, we could configure the graphics driver and/or Panda not to wait for video sync, and then it would run as fast as it possibly could. But you'd get tearing and other bad effects, and there's really not a lot of point in rendering faster than your video can anyway. This is actually good because this is time that other applications could be using the CPU if they wanted to. Panda's not being a greedy hog. All right. But here in bins, this is most of the time we're actually spending drawing triangles. So this is where the draw time is actually sending triangles down to the pipe, and that's still probably most of our time. And we can click a little closer breakdown still. How are we spending down those bins? Now in Toontown we have quite a few bins. Let me make this bigger so we can see it. I can't even read that. So on the bottom, the purple is transparent, and just above that is the fixed bin, and above that is the unsorted bin, and the big teal bin in the middle is opaque. And then we have ground as the top one, and there's a few fiddly little bins in the middle. But it looks like most of our time is spent here in transparent and in whatever that other one was, unsorted. This is probably Panda 2D right up here. This little one, unsorted bin, is mostly Panda 2D, or render 2D. So here's all our transparent objects. Here's the bulk of our work, of course. There's all the opaque objects, and there's some fiddly stuff in the bottom here. So if we're wondering where our triangles are going, well, okay, it's not surprising most of them are opaque. We're spending a lot of time drawing regular old opaque triangles. If we had other specialty bins and one of them was taking particularly long, then it'd be a good sign that something was unexpectedly wrong. But we kind of expect the opaque bin to be the biggest one. That's most of our scene. Okay, that's enough for a draw. Let's look at coal is not that interesting. There's not a lot we can say about coal. It starts at the beginning, which reverses a scene graph. It gets a bunch of data and sends it to draw. That's how long it takes. I don't think we can break that down much. Oh, there is one little thing. This one little category, show frame rate, show FPS. That's for drawing my frame rate meter up here. It doesn't show, it doesn't register, it hardly takes any time at all. But I put it in there just to prove that it's not taking any time. Okay, now the interesting one is app. Now for now, there's not a lot going on in here. Collisions, big chunk of our time. Animation, animating Mickey and myself. We're the only two people in the scene right now. These are the character animations. These are not things like intervals, which are moving the clouds around. Oh, the butterflies, those are animated too. And this is everything else. Everything is not categorized as one of the others. And these are all the Python tasks that we're haven't broken down right now. There's another little thing right here, that's PStats, and it does register a little bit. That's the time to generate the stats report itself.
Hey Dave.
Yeah.
What determines the order of the colors? Is it from the beginning of the frame to the end frame, bottom to top?
It's a good question. And the order is actually arbitrary. It's assigned by the programmer who defined these categories. And I'll talk about how that's done in a minute. And we'll also talk about how the frame is actually divided. But it does make a good segue. I say, we show, for instance, that we're spending X amount of time in collisions. That's not all necessarily contiguous. The frame might spend a certain number of milliseconds processing collisions, then do some other work, come back and do some more collisions, and do some more work, and then do some more collisions. And that would all be collected here, aggregated here into collisions, but the work that was not collisions that happened in between would be aggregated up here. And we can look at a little closer in, oops, no. Animation. We can look at the animation, for instance. This gets a little harder to read because it's so noisy. But these are the actual characters that we're seeing. So these are lists of all the characters. I see my dogs, my butterflies, there's Mickey in here. So I can see which characters we're actually spending all the time animating. And it, by convention, it collects together multiple characters that have the same name. So if I have multiple suits walking around, I'd see them all in the same category. all the same color band. Okay. And you guys see that I can change the scale of the graph by clicking on it and dragging up and down. It's a pretty handy thing to do, to looking it down. All right. Now, the other question is, how is the time actually spent in the frame? And that's what this other graph does. This is called a piano roll graph, and it's so called because it resembles the old piano player rolls, where imagine it reading through the piano this way. There'd be a perforated hole where you should play a note, and then it would stop when the note should stop. So if you imagine this feeding through the piano horizontally, and this represents a single frame, you can see at the beginning of the time, we spend some time in coal, then we skip over and do some draw, then we do some more coal, and then some more draw, then we do some, this is a flip, we do some other stuff which is off the scale. Let me scroll back a bit. In fact, let me pause it so we can talk about this. Okay, so here's one typical frame in Toontown. Now, this is interesting if you really want to see how things are broken down. It starts at the beginning of the frame, which for the purposes of PStats is whenever you call IG loop, a render frame. And that starts right here. The very first thing we do is, after a little bit of setup, we call the scene graph. We traverse through render 3D. Then we draw that. This, by the way, is the opaque draw bin. Happens at the same time as draw. What happens is, while I'm drawing at the high level category, I'm just doing draw, then part of draw is of course drawing the opaque bin. And there's also drawing the transparent bin and some other bins. All this is part of draw. After we've done drawing render 3D, we draw render 2D. Hardly takes any time at all. This is a little spec for render 2D. This is calling it, this is drawing it. Render 2D actually takes more time to call than draw, which is ironic. But it's not a whole lot of polygons and there's a lot of nodes, so it's not that surprising. And then we flip the buffers, we gotta wait for the video sync, and we come back and we start processing app. And this is all the app time. This is all the Python code that's going on. One of the things that Python does while it's running is, I think that's animation. Can't see it. Actually, this is part of collisions. This is collisions resetting all the transforms, and here's the rest of collisions. So it looks like we just have one contiguous collision traversal there. So that's a typical Panda Toontown frame. Pretty exciting, huh? Now this is not so exciting for a Python developer, because yeah, okay, I see cold draw, big deal. What I'm interested in is chaining all the stuff that's going on in Python. I know if I'm a Python developer, I don't care about everything that happens before Python. So there is an option in PStats to break this down into more detail, and I'll share that too. Actually, while I'm here, I just noticed these other little specs. These other little specs are all the characters that are animating. There's animate during call. So while it's calling scene graph, it visits each node, and if it visits a character, it says, oh, I need to animate that character. So it spends a little time doing that. And for the record, on the strip chart, the time spent in these little divots down here would be counted towards the character animation time, but not towards the call time, because they were stepping outside of call to do the character animation. It doesn't get counted twice, that is. And similarly here, this is the opaque draw time, which would be counted as towards the opaque bin draw time, not towards the aggregate draw time. But because the opaque draw is the child of draw, it actually still be shown in the big red graph at the top. That's a fiddly detail that I can clarify a little bit more if we're confused about it. But fair enough so far? Okay. I'm going to shut this down. Okay, and the option to turn on showbase task tracking is called PStats-tasks. I just turned that on. I'm going to run Toontown again.
Is the PStats server something you built, or?
Yeah. By the way, while I'm waiting for this to load, let me point out, if you run this on the same machine, of course, you are fighting for the same CPU, so you're degrading your performance a little bit more. That's part of what all the spikiness is. The reason the graph is so spiky is because the CPU is multitasking. It's doing a lot of different things, including drawing this graph. If I were running on a separate machine, and the machine that I was looking at was only doing Toontown, this graph would be a lot smoother, presumably. The other thing, too, is I found this to be true on Windows 2000 with a fairly sluggish machine. If I run Toontown, Toontown takes up so much of the CPU that it starves out my PStats server. So this graph doesn't even move at all, which is kind of unfortunate. So you have to be aware of that. If you're trying to run the graph on the same machine as your client, and the graph doesn't move, and you've got a sluggish machine on some broken OS, then that might be your problem. But if you've got a decent performance machine, and maybe XP is better than it, I don't know. It seems to work okay. All right. So I promised to show showcode better. So here I am in the app graph, and with an app I've got showcode. And as it happens, there's not a whole lot of showcode going on. It's very tiny down there, but I can zoom in on it. Make that window bigger again. Okay, so now I can see where my Python time is spent. And from the bottom, we got the event manager, is the graph on the bottom, processing the events out of Panda primarily. This is a pretty steady graph, so that suggests it's not really processing events. This is just the baseline, just to go through the loop and see there's nothing there. And similarly with this next one, which is something called manager. I don't even know what that is. Probably a task called manager. So this is just a task name. Whatever task name you give a task, this is what the name shows up here. Somebody created a task called manager and is doing this, whatever it is. Now, I'm curious. I'd have to go and look in the showcode and see what task manager is and what it's doing. But we can see it's doing something pretty steady as I'm just standing here. This is a pretty big one. This is eval loop, which is all the intervals. Actually, I know that this is moving butterflies around in the clouds and stuff like that. And then there's a lot of noise up here. But if I suspect a particular task might be expensive, what's one name here? For instance, update smart camera has traditionally been fairly expensive. I see right now it's not so bad. That's nice. Of course, I'm not moving. So let's see what happens if I start moving. So there, yeah, it gets a lot more expensive when I start to run around. So you can see, oh no, I'm not even running and it's expensive. It must be trying to bounce on the something behind me. Yeah. Right, so you can see here where I started to move, the smart camera started to do a lot more work. And here when I was just standing here, I was standing in a bad position, the smart camera was having to do some work. And now I'm standing still, it's happy, it's doing just the baseline stuff again. There's a lot of stuff that happens like that. Let me back up, for instance. Let's see, avatar controls is another one that's like that. Here the avatar controls is doing almost nothing. That's so small, I'm so happy. But I bet you, oh, it still does nothing. Maybe that task is not doing anything anymore. Well, okay. Good.
It's just fast.
Oh, here's another avatar control. Ah. So we've got two, somebody didn't quite follow the naming convention. The stats, the show-based task manager gets the name of the task. It actually takes a task name and drops off the hyphen series of digits on the end. Somebody created a task called avatar controls with a series of digits, but no hyphen. So that made it its own task instead of lumping it in with the other avatar controls.
That's not documented anywhere.
True enough, now it is.
Didn't see that between your ears.
And it's no crime, of course. But that means that the task I was looking at was not the task I thought it was. Yeah. Here's the real avatar controls, which is doing work now that I have to start moving around. But it's still not doing that much work. In the big picture, this is not so bad. And just for the fun of it, we'll bring up that piano roll again. Now, in this case, we've got so many tasks, the piano roll just runs off the top of the screen, and that's kind of unfortunate. There's a lot of tasks up there that's doing stuff, and you can't really see it all. But you can see here in the Python time, it's spending some time in various different tasks. Let me pause that. So Python has spent some time in this task, which is the collisions, then various different tasks. This one is another collision loop. So most of the time here is spent in collisions, not too surprisingly. Okay. There's one other interesting thing we can do. Some of the graphs we can bring up are referring to not just time, but things like texture usage. Let me unpause it. This is just an estimate, but this graph shows the amount of texture memory we've loaded and they're actually rendering right now. So this is based on just looking at the textures as they go by and calculating how much texture memory it ought to use up. We're not actually asking the card how much texture memory it uses. So certain cards may try to be clever and pack the textures differently. So your mileage may vary about your accuracy of this thing. But this is fun to look at. Close that other one, we don't need that anymore. If you need to, if you're questioning whether this Toontown will run on, say, an 8 meg graphics card, well, according to this estimate, we're not even close. We're looking like about 12 megs of active texture right now, and about almost 38 megs that are actually loaded in texture memory. In fact, Toontown does seem to run okay on an 8 meg graphics card. So it may be that the lower end graphics cards are compressing everything into 8-bit textures, for instance, instead of 16-bit textures or 32-bit textures. I think this is assuming 32-bit textures. But still, you can get a good rule of thumb. On at least a high-end graphics card, you're consuming about 12 megabytes of texture memory right now. And it says at the top here, the total loaded is 27. And as we run around, you can see that change. I'm a liar. Yeah, okay. So as I put more things in view, you can see, in particular, the bottom, the actual stuff that's being rendered right now changes. Looks like I don't really have a very high set of subset of my active texture memory. Yeah, there. I'm looking at most of the world there. So most of the things that are actually loaded are being rendered now. And you can ask things like vertices. How many vertices are you drawing? This is more interesting to watch as you run around. So as I'm looking over here in the corner, there's not much in front of me. I turn around to look at the whole world, I draw a lot more vertices. And in fact, you can see this correlate with the frame time too. You can see when the vertices dipped, so did the amount of time I spent in the frame. Which is good, that's what you expect to see. You want to spend most of your time drawing vertices and not doing wasted stuff. Exciting, isn't it? Okay. Let me show an application of actually using this to figure out what's going on with frame. I was looking at the CMU's Airblade demo. So let's run Airblade under PyPython or under PStats. Airblade is certainly a program that nobody has run PStats under because probably the CMU people haven't heard of it before. So it's interesting to see how it actually performs. Toontown is not as interesting because we've already spent a long time tuning it. Okay, here's good old Airblade. And the first thing I ask is, well, according to my frame rate meter, I've got about 18 frames per second here, when I'm only looking at a title screen, which is interesting. And the first question is, why is that? And looking at the graph, it looks like almost all that time is spent in draw, very little in app and call, which is good, I guess. Then I go down to draw, and there's well, again, we're looking at flip, a big chunk of flip, but also a big chunk of bins. It's actually drawing stuff. So I go over to the vertices, And son of a gun, I'm drawing 18,000 vertices there. So my guess is they've actually got the whole world behind the title screen, which is okay. It's just a title screen after all. But if they wanted to make this menu perform a little faster, they would probably be well off to hide that world while they're doing that. Now let's start the actual game. Okay, the game is going on in the background. And let's see. Again, I got lots of vertices going on, 15,000, 14,000. But most of my time is pretty well behaved. Almost all the time is spent in draw. There's a little bit of app time, not a whole lot. That's happy. I see things coming in and out of the vertices a lot. Let's take a closer look at app. Looks like there's a fair amount of show code, random Python code. Collisions is not too expensive. That's nice. Actually quite cheap, all things considered. I think it just died. So I've got 24,000 vertices in the scene, and my frame rate is about 15 or 16 hertz right now. So let's try that again. So Airblade actually is pretty well behaved, but it draws a lot of vertices. That's probably the biggest thing we got going on here. If I were wanting to improve the frame rate on Airblade, I would say, okay, maybe the first thing to do is put LEDs on some of these models, so you have some fewer vertices to draw when the models are far away. Well, in fact, what are these vertices? That's the next question. Let's see, base, toggle wireframe, base, toggle texture. So yeah, there's a lot going on in there. There's little swirly things. There's all vertices. My character, he's got a lot of vertices on him. So it's not surprising. We're drawing a lot of vertices here. But PStats is a useful tool to figure out why is the frame rate is not 60 hertz. The frame rate is low because we've got so many vertices in the scene. Okay. That's well enough for that. Now, the next question is, how do you use PStats? How do you do more than just look at things that I've already set up for you? If you wanted to time your own tasks, how would you take advantage of it? And what is actually PStats doing is the next question. Let me start with, let me start with what it's actually doing. In the code, we've got PStat collectors. And anytime you want to have a particular task that you want to time during the frame, you create a PStat collector, and you just give it a name. And by convention, I'm not sure if it starts with a colon, but it was, say, app foo, I don't know. So if you're timing something in app, you would call it app colon foo. That means to draw it in the big graph under the app category. That's all that it means, but it's an important thing to mean. If you just said foo, it'd be listed on the top graph along with app colon draw. Since I say app colon foo, it means it's subordinate to app. App won't see foo unless I click on app first. And any time it's spent in foo will be drawn as time spent in app. Now within a bracket of code in C++, typically I would have a PStat timer. And the PStat timer is just a trivial class who has no methods other than a constructor and a destructor, has no members. The constructor happens to call the collector.start, and the destructor calls collector.stop. So, although I don't recommend doing it, this is equivalent to doing it this way. Collector.start, collector.stop. The timer is just a convenience to make sure that I bracket the stops with the starts. So in general, when you have a piece of critical code, you bracket it with start and stop on the collector. Now what actually happens when you do that, the collector itself is a trivial class. It doesn't really have any data. It just has a pointer to the PStat client, and it has an index number. when you create the collector, it contacts the PStat client and asks it, the PStat client class, I should say, it doesn't actually do any network traffic at this point, and asks it to define a collector called @:foo, and the PStat client allocates the space for that and gives it an index number. Meantime, the PStat client is building up a list of all these collectors. There'll be foo, and of course there'll also be draw and other things. Each one has a different index number. And each time I call start, actually, yeah, it's building during at the beginning of the frame. The PStat client clears its buffer of events, and each time I call start on something, it records an event. It gets the clock time from the global clock, get real time, and records that as an event in a big array. And when I call stop, it records another event. It doesn't actually do any subtraction, any aggregation, anything like that. All it does is record events. So when I call collector.start, it just says, okay, collector @foo started at this time. Then later I call collector.stop, it says, okay, collector @foo stopped at this time. And of course I got other collectors that are starting and stopping all this time. This is all designed to be very low overhead, so that all I have to do is query the clock here and record one more entry into a vector. Relatively quick. At the end of the day, we've built up a whole big vector of these things. Lots of starts and stops in no particular order, representing the whole frame activity. All it does is build a big datagram out of this, packages it up for the transmission over the TCP, and ships it off to the PStat server. Still doesn't do any analysis, and then it clears it and starts over again for the next frame. All the analysis is actually done on the PStat server. The PStat server gets this big array for a given frame, looks at the collection of starts and stops, figures out how much time was spent in each collector, and draws a graph for you.
Let's do with the text string.
The text string, yes. That is actually shipped at the beginning. When the connection is initially made to the PStat server, it says, okay, here's all my collectors and here are the names. And so the server gets the name and the associated index.
So you got to make your collectors global so they can forward declare before you establish the PStat connection?
Actually, it can define them on the fly. And when it does, it just sends another message. Oh, here's some more collectors.
Okay, so sitting on the string.
Yeah.
Cool.
Actually, it does a TCP UDP thing. It sends most of these packets over UDP, but critical things like the collector names it sends over TCP. So, pretty simple. Again, an important thing is that it's designed to be as lightweight as possible. And normally there would just be a PStat timer, so you don't even have to think too much about it. And this is nice because if you return or do something else out of this function, you don't have to worry about calling stop implicitly. And it's also designed so that if you're compiling opt4, this class just goes to nothing. It compiles to nothing. It turns into a bunch of inline methods that have actually no bodies. So the whole thing goes away altogether. It may happen that you want to compile opt4 and still compile with PStats. There isn't a pre-make option to do that. I don't know what it is. We can look it up. So, but in general, by default, when you're compiling opt4, PStats is disabled. So we ship Toontown without PStats.
How does the polygon count?
Ah, that's another question. Yes. This is for counting time. The collectors also have a method called increment. I think it is something like that. There's increment values. Or no, it's add value. So every time I draw a triangle, basically I call collector add value 1. And at the end of the frame, I call collector, or I should say at the beginning of the frame, I call collector set value 0. And again, this just gets recorded in this big event list. So this is for numerical values that's not related to time, but still it gets boiled down in the event list. This is a little bit of a simplification. I don't draw triangles one at a time. I might draw 100 at a time or something like that. But basically, I create an event that says add value this number to my running total. And that gets packaged up and shipped off to the server at the same time. So at the end of the day, it has the total number of triangles that I've drawn. There are some other things. The texture memory, I just, add value and subtract value every time. Some things I just do a set value every time when I know the new value. I'm not sure what those examples would be. Okay. Now, this is all in C. If I'm a C++ programmer, that's great. If I'm a Python programmer, the same rules apply. I still create a collector, and I can create a collector dynamically anytime I want and give it any name I want. And that's in fact how we're doing the task management. When you say want PStats, what it does is it runs some additional Python code that every time you spawn a task, it creates a collector for that task given the task name. And then it calls start and stop at the beginning and end of the task. Now the PStat timer isn't published. It could be, but I think it'd be a bad idea because it'd be a little misleading. For one thing, in Python, creating the PStat timer would be expensive. It's not free like it is in C. And for another thing, I'm not entirely sure that the thing would go away at the end of the scope. I mean, it's supposed to. It's Python's reference counted, but I might decide to keep it along a little bit longer. You want to be able to time it accurately. So I say if you're running Python, you explicitly call collector start and stop. But those methods are published, so you can call them explicitly. And one nice feature of the collectors, by the way, if you have multiple collectors with the same name, they're considered to be the same collector. So you can start and stop them independently, and it will still count towards the same time. It's the same total. That's how we collect together the multiple tasks. A lot of times we have in various tasks, for instance, the look at task. There's a look at dash the number of my avatar, my do ID, and then somebody else might be running a look at task. He's got the look at dash his avatar ID. I really don't want to see those separately. I want to lump those together. That's how it takes a dash digits after the end of the name and throws that away and passes that to the name. So I end up with one collector called look at and another collector called look at. Two different look at collectors for the two different look at tasks, but they're considered to be the same collector and they're lumped together.
If you overlapped the starts and stops from two different collectors, would it double up the time?
It would yell at you. The server would actually yell at you. The PStat client wouldn't notice because it's just dumbly sticking this in the packet. But it would get shipped off to the server, and the server would print error messages saying, hey, this was started when it should have been stopped. It also yells at you if you start a task and don't stop it at the end of the frame. Things like that. So, let's see. I don't think there's anything else to say. There's a little bit more. Yeah, a little bit more is Darren asked about how the things are ordered, and also along with that same line is how you specify the color that these are. That is all specified by the Panda client, not by the PStats server. And right now there is a single file in the PStat client directory that it's basically just an array. It lists all the collectors we might define and defines a color and an ordering sequence for them. And that's a terrible way to do it. One day I'm going to fix that, but for now that's the way it works. And if you happen to create a collector that's not on that list, it just assigns a random color to it and gives it a random ordering. But the purpose of that table is to just list all the things that you're commonly going to define in a common color for them so that they come out the same color every time, and you put it in a sensible order. I wanted to put them in one place because it's nice to see that list in one place. But it means we've got some Toontown things in there, and some direct things, and some Panda things, and it's all in the wrong place. So we need a better system for that. But for the moment, that's how it is. There's one C file that just has a big array that lists those things. Roger, you're going to ask?
Oh, so if we're looking at the AI, and we debug that, the method to use PStat, make sure I get this, is you go in and you crack your epoch, your main loop in pieces, and start conquering and dividing till you find the magic thing you're looking for.
Yes, we could absolutely do that on the AI. Yep.
What timer are you using on Windows that's giving you this fidelity?
It's called the Query Performance Counter.
Okay. Penny and block timers.
Yeah. Yeah, that's the same timer we use everywhere in Toontown and Panda in general. Yeah, so PStats is not actually tied to the rendering. You don't actually have to be rendering a frame in order to get meaningful data out of it. You just have to have somebody to call PStat client tick every frame, whatever frame is, and to call start and stop. And actually there is rudimentary support for threaded PStats where you can have multiple threads doing different things at the same time. Since Panda itself is not really threaded, the threaded support for PStats is untested and probably is buggy. When we eventually add threading to Panda, then that'll get exercised, and we'll be able to flush that out. But the framework is all there. Yeah, so PStats is particularly useful for doing top-down analysis of your frame. If you want to do bottom-up analysis, that's where you can use your profilers and tools like that. PStat won't help you too much with that. But it is pretty useful to see where is most of my time going. Yeah.
Just to mention it, without having PStats before, there's a profile timer and a delta profiler in C++ and in Python that do very similar things that are far simpler and don't have servers and just print out text.
Yes. Yes, they are handy. PStats sprung out of a similar program that we had when we were doing the Herc and Aladdin games. And at that time, we didn't have tools like that. We had, I mean, there were profilers, but profilers don't give you the top-down analysis, and sometimes you really want the top-down analysis.
Which real-time profiler you're using?
No, it's not a pro. It's basically a thing just like PStats, except it doesn't run a client server. It stores its stuff up in an array. It's something I just, because I've used profilers before and I haven't had these, there's a little pattern of code that I just more or less have memorized. It's only about a page or a page and a half of text that whenever I want to do this, at each new place I work, I just type it all out and I start using it.
And it has runtime as it's running, it indicates? Or?
Yeah, it does the same kind of, no. It stores it up and then it dumps it to a text file.
Oh, okay.
It's a lot of the same architecture instead of
okay.
client server. At the end of it, it spits it out to the log instead of sending it to the server. Yeah.
Yeah. It is pretty
it's a
nice.
miniature version.
It is pretty nice to see that scrolling strip chart go by, and to see as you're running through the world to see things change. That's nice, and to be able to drill down to get the level of detail that you care.
How heavyweight is the collector, the network bandwidth, and all that other? I mean, if you decide to put PStat in other tools, it's a pretty ingenious little section.
Yeah, it could be done. The biggest part is pulling out Panda, I guess. Separating it from the Panda build. I mean, it does take advantage of tools that are in Panda, the net client, for instance, NSPR.
Yeah,
like that.
forgetting that. But it looks like the protocol's simple enough. If you had to, you could just call the protocol.
Yeah, that's true.
But the feeling for the call, I found that in the servers it was real expensive to call get time and get clock and those things. You only do,
Yeah, that's true. It is.
It shocked me the amount of overhead those type of calls cause. And Linux is one of the big offenders.
Yeah, yeah.
Yeah.
No, it is, and it's expensive in Windows too to get the opinion clock. But what are you going to do? You have to get that timestamp at some point.
How much data is it throwing back and forth across the wire? Is it a lot?
It's relatively little and tries to keep it down. There's actually a parameter to limit the amount of data that you throw, so that if it sees, I think it's set to.
Well, GDP. So is it cross packets?
I'm sorry, I don't know cross.
It's UDP, right?
Right.
That you're sending this bulk data?
Yeah.
And you only send 1 datagram per epoch?
One per frame, right?
Okay, so one minimum you're limited to packet size.
Yeah, that's true. Yeah, that's in fact that's
It's very big on localhost, but kind of limited on.
Right, that's what the limiting factor is. Packet size per frame, at least. You can limit it even smaller. You can limit to a certain number of bytes per second. And what it'll do is it'll just discard frames instead of throwing them across the wire. It'll collect them and then discard it.
That's pretty cool.
In fact, that may be one solution. If you're trying to run PStat on the same machine that you're running on, and it's a very slow machine, and your PStat server is disturbing, you can set the limiting very high. So, or very low, rather. Yeah, so it sends very few frames over, and then your server can run. Okay, thanks, guys.